Section 12.2, Vectors. So to review, a vector indicates a quantity such as displacement or velocity or force that has both magnitude and direction. Now you've definitely seen vectors before. We might not have called them vectors, but a good example of this is velocity. So speed indicates how fast something is going, but then when you get into velocity, velocity indicates how fast something's going in a certain direction. So that's all a vector is. We often represent a vector with an arrow or a directed line segment. In general, the longer this arrow is, the higher that magnitude of the vector, and the direction of the arrow is obviously the direction of that vector. So we can use two different things to denote vectors when we're talking about them. We can either put this letter, the name of the vector, in boldface, or put an arrow above it. And you'll see me generally write something like this, just because it's very difficult to write in boldface. So you're going to just want to put an arrow, or at least sort of an arrow above that letter to show that it is a vector. So suppose a particle moves along a line segment from point A to point B. So this is the corresponding displacement vector. Displacement just refers to some sort of movement that has initial point A, which is the tail, and terminal point B, which is the tip. Just be careful with this. It sounds a little bit strange, but vectors start at the tail. And we indicate this by writing that this vector is equal to AB. So just making sure you're going, these letters are in the sequence of the vector. So we're going from A to B. This vector is going from A to B. So with vectors, BA is not equal to AB, because BA would be in the opposite direction, going from B to A. Now remembering that vectors don't have any kind of starting point, a vector only takes into consideration the direction and the magnitude. This vector CD, it has the same direction, this arrow is the same length, so we're assuming it has the same magnitude. And although A and C are different starting points, we can say that U and V are equivalent or equal. It does not matter which. All right, there is the 0 vector, denoted by 0, and it has a length 0, and it's the only vector with no specific direction. This will come into play in some of our calculations later down the line. So we can combine vectors geometrically. So suppose a particle moves from A to B, so the vector is AB. Then the particle changes direction and moves from B to C. That means that we have a displacement vector BC. Now the combined effect of these displacements is that the particle moves from A to C. So if a particle moves from A to B and then from B to C, obviously the particle ultimately goes from A to C. So this is the resulting displacement vector. And we can find this mathematically by adding these two vectors. We can say that the sum of these vectors AB and BC is equal to the total displacement of, whatever particle we're talking about from A to C. So this brings us to vector addition. If U and V are vectors positioned so that the initial point of V is at the terminal point of U, then the sum U plus V is the vector from the initial point of U to the terminal point of V, which is just a very technical way to say that we can add two vectors if the first vector ends where the second vector starts. So we need this point B in here to be the terminal point of A and the beginning of that B. All right, so we can create this sum geometrically if we are given specific vectors. You can see why this is sometimes called the triangle law, because if these vectors aren't facing the same direction, the displacement vector often forms the third side of that triangle. Now there's another way to construct these vectors, and this just shows that u plus v is the same as v plus u. And this idea, think about this logically. If a man walks north 3 miles and then east 5 miles, so north 3 miles and east 5 miles, well, isn't that the same exact thing as if he walks east 5 miles and north 3 miles? So we're just saying the same exact thing with vectors. All right, so let's do an example. Let's start by drawing the sum of these vectors A and B. And we can do this 2 ways. We've got 2 different types of constructions. We can use our triangle construction or our parallelogram. So starting with the triangle, if we want to add A and B, we are going to put the tail of one vector on the tip of the first. So if we want to say, okay, A plus B, I'll start with vector A, and I'll do my best to draw vector A exactly as is. I understand my angle's a little off. We're trying our best here. And then on the tip of A, we're going to put the tail of B. So now B is going to be here. And now our question is, remembering that we started at the tail of A, what is the sum of these vectors? Well, that goes from the tail end of A to the tip of B. So this is our sum A plus B. All right, and for our parallelogram, let's start at some point, and what we're going to do is we're going to draw both A and B coming off of the same point. So B faces down this way, and A faces this way. And then our parallelogram states that if we take this and construct that parallelogram, then the diagonal of that parallelogram will be the resultant vector. So now on the tip of B, I'm going to attach A. So I'm going to draw A. And on the tip of this A, I'm going to draw B. All right, and that is supposed to be a parallelogram. A little bit better. All right, so now this diagonal from where I started across is the resultant vector A plus B. And while the drawings are not perfect, you can see our angle is a little bit different. We do get the same vector either way, using either method, triangle or parallelogram. So now we're going to talk about scalar multiplication. So it's possible to multiply a vector by this real number c, which we call a scalar. So a scalar is just different from a vector in that it's just some number. It doesn't have a magnitude and direction, it's just a number. So if c is a scalar and v is a vector, we have this bold-faced v, then the scalar multiple, c times v, is the vector whose length is the absolute value of c times the length of b, and whose direction is the same as v, if c is positive, and opposite is if v is negative. So let's just go through some examples here. If we have some vector v, we can find 2v by just taking v in the same direction and doubling the length of it. So this is how we get 2v. We get 1/2 v by halving the length of v. Again, both of these are in the same direction because this v is positive. Now in the case of a negative, what we do is we just flip the direction. So if this v is going up and to the right, this negative v is going to go down and to the left. And same over here. In this case, we have this negative, and so we flipped the direction of v. Multiplying that by 1.5 means we are taking this v and then adding another half of that length to this vector. So this is how scalar multiplication works. Now, what does this help us do? This helps us to subtract vectors. If we want to subtract vectors, we are really just adding the second vector in the opposite direction. So let's do an example of that. How about a minus 2b? To find a minus 2b, we're really going to take a, and then we're adding a negative 2b. So we need to find negative 2b. Well, when we negate this vector, we're just saying that it's traveling in the opposite direction. So instead of down and over, it's going to be up and over the other way. And multiplying it by 2 means we're doubling the length of b. So negative 2b is going to be in the opposite direction as b, and it's going to be twice the length of b. So this is our negative 2b. So now we can use both the triangle and the parallelogram methods to draw this a minus 2b. So we're starting with a, and I'll start down here. We're starting with a, and then on the head of a, on the tip of a, we are then going to attach the tail of negative 2b, meaning from a, we're going to draw up 2b, negative 2b, and then our resultant vector goes from the tail of a to the tip of this negative 2b. So this is the resultant vector a minus 2b. All right, let's use the parallelogram method. Using the parallelogram method, we're going to draw a and negative 2b starting from the same point. So we will draw a and negative 2b starting from this same point, and then by forming a parallelogram, the diagonal of this parallelogram will form our resultant vector. So this diagonal is our resultant vector a minus 2b. And despite the handwriting, which is a little rough on my end, you can see that a minus 2b is the same vector. It's facing in the same direction, and it's got the same length if we drew this perfectly. So in example 3, we just have a few constructions. So what I want you to do is pause this video, try out these constructions using whichever method you would like. You don't have to use the triangle and the parallelogram method. They're just options, whichever one just kind of works for you a little bit better. So pause this video, go through these, and then unpause and I'll go through them. All right. So let's start with A. We are adding u and w. Now, I'm going to use the triangle method, but if you choose to use the parallelogram method, you should get the same resultant vector. So adding u and w, we are going to start with u, and then to the head of u, we are adding the tail of w, and from the tail of u to the head of w is our resultant vector u plus w. For B, Now we are taking W and subtracting V. So that means we're doing W plus a negative V, which means we're starting with W. And then negative V is going to be the same magnitude as V, but in the opposite direction. So this arrow is going to be the same length, but in the opposite direction. So this is going to be our negative V. And we have the resultant vector, W minus V. All right, for C, we have U plus V plus W, meaning we're starting with U. And then to the end of this arrow, we're adding V. And to the end of V, let's keep ourselves organized, U, V, then we're adding W. And so we have the resultant vector, U plus V plus W. One more D, we have U minus W minus V. So again, we're starting with U because that U is positive. Now we're subtracting W, which means I'm going to draw W with the same magnitude but in the opposite direction. Okay, this will be a negative W, and then a negative V likewise is going to be the same magnitude as V, so the same length of the arrow but in the opposite direction. So then we're going to have a negative V. And so your resultant vector, U minus W minus V, is going to look something like this. All right, I'm sure you guys did great on this activity. If you did not, I have 6 office hours throughout the week, and I'd love for you guys to come visit me on Zoom. So now let's talk about components. In the beginning of this section, so with these vectors that were just labeled as a capital letter and just went somewhere in the 2-dimensional plane, we've just kind of been working with abstract examples. So now let's throw this idea on the coordinate plane. So we're going to look at this algebraically. If we were to draw an arrow, right, from on a 2 and a 3-dimensional coordinate system, on a 2-dimensional, from the origin to some point, we know that the terminal end of this vector A would just be our coordinates. Same in 3-dimensional system, right? So we're just saying if we draw an arrow from the origin to any point, well, now we're going to call this a vector. And we have coordinates that are called components of A when they're in the form of a vector. So when we're talking about this direction, not just where this point is on a plane or in space like we have done previously. So we can denote this A as A sub 1, A sub 2, or A sub 3 with the X, Y, and Z components. So vectors, you know it's a vector if it's surrounded by these kind of arrow, these pointy brackets. We know it's a point when it's surrounded by our parentheses. So what they have in common is that the terminal point is reached from the initial point by a displacement of 3 units to the right and 2 units upward. So we have the point 3, 2. And so this is our vector, our arrow, because we're going right 3 units and 2 upward. But this is also the vector 3, 2, because again, we're going 3 units to the right and 2 units upward. And remember we said at the beginning that it does not matter where your vector starts. It just matters that it's in this direction and with a certain magnitude, and we'll find magnitude algebraically later. But all we're really saying is that we can think of these, geometric vectors as a representation of the algebraic vector, because algebraically there are an infinite number of potential geometric vectors, right? Because no matter where we start, if we go 3 units to the right, 2 units up, great, that's a vector 3 too. So we just have an infinite number of actual geometric vectors. So algebraically, we're just giving a representation. All right, so the particular representation of this vector from the origin is called the position vector. That just tells us the position of this point if we were to start at the origin. And this is for both 2 and 3-dimensional systems. All right, so how do we find the vector from one point to the next? Well, it's fairly simple because we just want to find the change in x, the change in y, and the change in z components. And so we can say that any vector A going from points A to B can be represented by taking this, again, we have these pointy brackets here, the difference in x values, the difference in y values, and the difference in z values, because again, vector, we just want the change. We just want the displacement. We're not concerned with where this starts. Example 4, we're going to find the vector represented by the directed line segment with initial point A and terminal point B. So we are going from A to B, and so we can call that vector AB with an arrow over it. And if I was typing this out, I could also just call that A and B in bold. But handwriting, I'm going to put an arrow over just to make sure I know that this is a vector we're talking about. And another thing we know with a vector is that we have these triangle braces here. So now my components are just going to be the change in x from A to B, meaning I'm taking this point in B and I'm subtracting that point in A to get the change in x. I'm going to do the same thing with my y values, starting with the terminal point and subtracting the initial point. And same thing with my z values, from the terminal point and subtracting from this initial point. -2 minus 2 gives us -4. 1 minus -3 gives us +4. And 1 minus 4 gives us -3. So this is going to be our vector AB. Now the magnitude of a vector is just its length, and we can denote that by putting it looks exactly like the absolute value symbol around that vector. Sometimes we have these double lines around the vector, but we generally use this first notation. So here, to find the magnitude of the vector, we're using the distance formula, because remember, from the vector, we really just want the distance from the starting point to the terminal point of this vector when we're talking about a distance of, what we would represent as an arrow. So if A is this vector from x component being 4, y component being 0, and z component being 3, we want to find the magnitude of A. So we're going to do that by using this sort of distance formula, because what we're really saying is, if I have my 3-dimensional coordinate system, all right, this A can be represented. Now remember, we have an infinite number of potential vectors because we're just talking about distance, but say we start at the origin, right? This vector would be the distance from this origin to the point 4 in the x direction, 0 in the y direction, and 3 in the z direction. So this would be some point P, which we would call 4, 0, 3. Notice I'm using parentheses for this point P. But this vector is going to be the distance from the origin to this point. And while this arrow looks really short, it's sort of coming at us and then up. So it can be a little deceiving in 3 dimensions, but we want to find the distance of this arrow, and we're starting at the origin. So what we're really doing It's kind of like we're saying, okay, the distance in the x direction is 4 minus 0, which is 4. In the y direction, it's 0 minus 0, which is 0. And in the z direction, it's 3 minus 0, which is 3. And that's how we get this length of the three-dimensional vector, because we're really subtracting this point from the origin, right? So we're finding A, the magnitude of A, being equal to the square root of 4 squared plus 0 squared plus 3 squared, which is equal to the square root of 16 plus 9. We know the square root of 25 is just 5. So the magnitude of A is 5. That means the length, the actual length of this arrow would be 5 units from the origin to this point P. So this is the magnitude of our vector. So now for some algebraic rules of vectors. Now we can combine vectors with addition by just adding their components. So a plus b is just going to be a1 plus b1, meaning we're going to add the x components, and a2 plus b2, meaning we're adding the y components. Because when we have a sum of these vectors, we want to retain the fact that we want to find the displacement in the x direction and the displacement in the y direction. We shouldn't just get some magnitude. We want to find completely the direction of the displacement vector. So we're just adding corresponding components. The same idea goes for subtraction. So there are a bunch of different rules we can follow. Now to multiply a vector by a scalar, and again, a scalar just means there is no direction, it's just a magnitude, and that's going to look like a constant for us. We're just multiplying each component by that scalar. So you can see that if we have the vector A that's multiplied by C, we're just multiplying that horizontal and that vertical component by C. So we have a few rules here. This is what we just stated. Now the same applies for three-dimensional vectors. When we add, we're just adding the components. When we subtract, we're just subtracting the components. And the same thing for multiplying scalars. But here are a few other properties of vectors. Now we have that a plus b is equal to b plus a. And we showed that at the beginning of this section with our parallelogram law. Our parallelogram law showed that it did not matter which vector was first. When you add two vectors, you get the same resultant vector. And, in plain terms, this would be called the commutative property. All right. Number 3, if you multiply a by if you add a to a 0 vector, this is where a 0 vector comes in, nothing happens to a. That makes sense, right? If you add 0 to anything, you just get what you originally added 0 to. If you multiply a scalar by the addition of two vectors, you're just distributing that scalar to each of the two vectors. So this is kind of like the distributive property. Number 7, if I multiply, so in this case C and D are scalars, and A is a vector. I know that because A is bold and C and D are not. If I multiply two scalars by a vector, well, that's the same thing as multiplying a scalar by a scalar times a vector. Essentially saying that it does not matter in which order we multiply scalars. Now this is only true because C and D are both scalars. All right, and this is the associative property. Number 2, I realize I'm not exactly going in order, sorry about that. When we add A to the quantity B plus C, this is the same thing as adding A and B and then adding C, and this is called the associative property again. When I add A to negative A, I just get that 0 vector. That makes sense, right? Number 6, when I add two scalars, C and D, and multiply them by a vector, it's the same thing as taking a scalar times that vector and adding the second scalar times that vector. And this would be the distributive property as well. Finally, 1 times A is just equal to A. Great. that makes sense. Now we don't need to know what all of these properties are called. This just shows that a lot of the properties that we know and love from algebra also apply to vectors. So now let's use some of these in a few examples. So we want to find a plus b, 5a plus 3b, the magnitude of a, and the magnitude of a minus b. All right, starting with a plus b. To add two vectors, we are just adding their components, meaning a plus b is going to be a vector in which the first component is -2 plus 4, just adding the x components, and then the second component is going to be 5 plus a -3, just adding those y components, and simplifying this will give us +2, +2. So this is our vector a plus b. Not too bad. How about 5a plus 3b? Well, remember, when we multiply a scalar times a vector, we are just multiplying the scalar and each of those components. And so let's do that first. Let's take 5a. So we're taking 5 times the vector -2, 5, plus 3 times the vector 4, -3. Well, this is going to be 5 times -2, which is -10, and 5 times 5, which is 25. We are adding to that 3 times 4, which is 12, and -3 times 3, which is -9. Remember, multiplying by a scalar, we just multiply that by all the components. And now finally for the addition, we're just adding each of the components. -10 plus 12 is 2. 25 minus 9 is 16. So this is 5a plus 3b. For the magnitude of a, what we're kind of doing is we're kind of saying, okay, what is the distance from the origin to the point 2, 5 on a coordinate plane? And so we're using a modified version of the distance formula and just getting that first component, squaring it, adding to that the second component squared. All right, this is going to give us the square root of 4 plus 25. And let's call that the square root of 29, which cannot be simplified. Finally, we have the magnitude of a minus b. And when we get into more complicated operations, we're just going to use kind of our order of operations here. So we're going to do what's inside of this magnitude symbol first. And so we're going to start by finding a minus b. So a minus b is what happens when we take -2 and subtract 4. Just taking the component of a, subtracting from that the component of b, and then 5 minus -3. And so a minus b is -6 and 8. Now we can take the magnitude of a minus b. So the magnitude of -6, 8, which is the square root of -6 squared, plus the square root, just plus 8 squared. 36 plus 64 is 100. So we get the square root of 100, which is equal to just 10. All right, so the magnitude of a minus b is just 10. So now for our standard basic vectors. So we can call these components I, j, and k. So we have these standard basic vectors with a length of 1 that just say that, okay, I is a vector with a length of 1 lying on the x-axis in the x direction. J is a vector with a length of 1 lying on the y-axis in the y direction. And k is a vector with a length of 1 lying on the z-axis in the z direction. And I know in other classes you use I to denote imaginary numbers, and this is not one of those times. So I no longer means an imaginary number for this section, so don't let that confuse you. So what this allows us to do is it allows us to write this vector just in a different way. So with the same three components, but instead of putting it in these pointy brackets, we can attach the x component to our I, the y component to j, and the z component to k. So we're really just writing these vectors a little bit differently. That means that this vector 1, -2, 6, for example, can be written as I, meaning 1i, minus 2j, plus 6k. So you see we're really just taking these components and writing them in a different way. This is no longer necessarily in vector form. A lot of our answers throughout, several sections of this chapter in general can either be written in one of these two forms. WebAssign will be really clear on which form it wants you to write it in, so just make sure you can write it in either form. Alright, the same obviously applies for 2 dimensions, so let's look at an example. Given that A is I plus 2j minus 3k and B is 4i plus 7k, express 2a plus 3b in terms of I, j, and k. So 2a is what we get if we multiply this 2, this scalar, by every component in A, in this vector. So 2 times I is 2i, 2 times 2j is 4j, and 2 times -3k is -6k. So same thing here. What about 3b? Well, we're just multiplying each component by 3. So we get 3 times 4, which is 12i, plus 3 times 7, which is 21k. All right. Now the only thing that's missing that might trip us up with this 3b here is that we don't have a j component. And so we can really rewrite this 3b as 12i plus 0j plus 21k. Not that we need the j component, but this is just a placeholder to make sure we don't add the wrong components when we do this addition. So when we have 2a plus 3b, we get this 2a. So 2i plus 4j minus 6k, and now I'm adding 12i plus 0j plus 21k. Now, like with the other form of vectors, we're going to add like components. 2i plus 12i is 14i. 4j plus 0j is 4j. And -6k plus 21k is going to be positive 15k. And so 2a plus 3b is 14i plus 4j plus 15k. Now this is doing the same exact problem we did before, except instead of this form, we are writing it in this form. We're just kind of switching our representations of these vector operations. We're not doing anything different here. So now a unit vector is a vector whose length is 1. So I, j, and k are all unit vectors. So we converted all of these to unit vectors because they have a length of 1. Now in general, if a is not equal to 0, then the unit vector just has, well, and this just means if the vector isn't a 0 vector, then the unit vector is going to be 1 over the magnitude of a times a, which just gives us a over the magnitude of a. So to find a unit vector, we're just taking that vector and dividing it by the magnitude of the vector. And this will give us a vector that is a length of 1 in the same direction as this original vector. All right, so let's find this. So we want to find the magnitude of this vector. So to find the magnitude of 2i minus j plus 2k, we're going to take the square root of this quantity 2 squared plus, we have a negative j, so that y component is negative 1 squared plus our z component is 2 squared. Alright, and we take the square root of all of this, then we get 4 plus 1 plus 4, which is the square root of 9, or 3. So now, what we're doing is we're taking a, this original vector, and dividing it by the magnitude of a, so dividing it by 3. So we are taking 2i minus j plus 2k and dividing it by 3. This gives us a unit vector, and I'm going to call this u just to show that it is a unit vector. Because I can't write in bold, I'll put an arrow there. So our unit vector is going to be 2i divided by 3, which we can call 2/3 I, minus j over 3. So minus 1/3 j plus 2k over 3, so plus 2/3 k. So this is our unit vector. Now if we wanted to check that it's a unit vector, what we would do is we would take the magnitude of this unit vector, just to make sure it's 1, because that's what the definition of our unit vector is. So if we take the square root of 2/3 squared plus negative 1/3 squared plus another 2/3 squared, we would get 2/3 squared is 4/9, negative 1/3 squared is 1/9, and then we have another 4/9. And we can see that 4/9 plus 1/9 plus 4/9 is just 9/9. Square root of that is equal to 1. Great. So we have just checked that this is in fact a unit vector. So now for our applications, we're going to see where vectors are really useful. And they're very useful in physics engineering because generally in a real world situation we have several different forces acting on an object. Generally, we'll have forces in the horizontal direction, this is in 2 dimensions, and forces in the vertical direction. In 3 dimensions, I mean there are forces in all 3 directions. Generally, if we're talking in 3 dimensions, we will have a force in the negative z direction of gravity. In 2 dimensions, it's going to be a force in the negative y direction. So using vectors for things like that can help us separate these different components. So if several forces act on an object, the resultant force is the vector sum of these forces. So we learned that earlier. Generally, we're going to look for perpendicular components, like the horizontal components and the vertical components. So if we have this right triangle here, all right, and we have this as some angle theta. Now, in this little key here, we are going to call the hypotenuse a resultant force R, so we'll just put an R there to denote the hypotenuse. How do I find U? Well, I know that the cosine of theta is equal to U over R. All right, how do I find V? Well, I know that the sine of theta is equal to V over R. So how do I isolate U and V? Well, I can multiply both sides by R, and I get that U is equal to R times the cosine of theta, and V is equal to R times the sine of theta. And so this is the horizontal component, and this is the vertical component. And for the scope of this class, we're just going to be worried about solving application problems with vector forces in 2 dimensions. 3 dimensions is definitely doable, but it can get to be a little bit crazy. So we're going to generally use these 2 formulas. Now, what does this look like? This might look really familiar. That's from polar coordinates. Remember, when we switched from polar coordinates to Cartesian and vice versa, we saw that x is equal to r cosine theta and y is equal to r sine theta. So we're using this same idea because now we have, in these problems we have this angle that the forces are oriented from the origin. So this should look a little bit familiar. So let's do an example of this. We want to find the magnitude of the resultant force and the angle it makes with the positive x-axis. So A is going to be 100 newtons and B 400 newtons. So looking at this geometrically, we can say that A has a resultant R of 100 newtons and B has a resultant R of 400 newtons. Okay, now 100 newtons is really the magnitude of this force A. So what we want to do is we have the magnitude of A, and we want to find out what A is really doing as far as the vertical and horizontal components. So we want to take A, using the fact that this angle is 60 degrees, and find the vector that represents A. So we just have a magnitude and angle. We want to find the vector that represents A. Well, in this case, because my magnitude is 100 newtons, that really means my R is 100 newtons. So for A, my R is 100 newtons. And I know this is in newtons, so I'll just forgo the units for now. That means my horizontal component is going to be 100 times the cosine of theta, which is 60 degrees. Well, 100 times the cosine of theta is 100 times 1/2, which is going to be 50. All right, now what is my vertical component? My V is going to be that same R times the sine of theta. Now the sine of 60 is root 3 over 2, so we're going to have 100 times root 3 over 2, which is 50 root 3. Okay, so I can write A as a vector, and to show that it's a vector, I'm going to put that little vector symbol. And I can say that this is equal to the component in the x direction is 50, and the component in the y direction is 50 root 3. And we'll make sure we have our units in at the end. So now what about B? Well, B is a little bit easier because B is a horizontal force, and we're only traveling in the negative x direction, meaning that my U is really a negative 400, and my V is just 0. There's no vertical component of B. And so to get my resultant force, I want to find A plus B. And let's just put B in vector form first. So the vector B is going to come from the horizontal component of negative 400 and the vertical component of 0. So now that we have A and B in vector form, now we can add them. We know we get a resultant force by adding vectors. So vector A plus vector B, I can get by adding each of the components. 50 plus negative 400, and 50 root 3 plus 0. Okay, so the resultant force is negative 350, 50 root 3. But we're not quite done yet because we want the magnitude and the angle it makes with the positive x-axis. So now can I take this and use these ideas to find the angle and the hypotenuse? So we've really found the resultant force. And what this looks like is if I plot this on the x and y axis, just going to be kind of a rough plot. This means that my x component is negative 350 and my y component is 50 root 3, which is smaller than 350, so it's going to be something like this. So this is my resultant force, this vector of A plus B. Okay, and in the negative x direction, we've got 350. And in the y direction, we've got 50 root 3. All right, and I'm keeping this positive because now I'm just talking about these lengths on the side of a triangle. Now, how do I find this angle? Well, I have the opposite and adjacent sides, so I can use tangent. So the tangent of theta is equal to 50 root 3 over 350. And so I can say that theta is equal to the arctangent of, well, I can simplify this to be root 3 over 7. And when I plug that in the calculator, we get approximately 13.9 degrees. And let's look at the question. We want the angle it makes with the positive x-axis. If theta is 13.9 degrees, we really want this angle. I really should have stopped right at this point. We really want this angle here. Let's call that alpha. Now, how do we get to alpha from theta? Well, we know this is 180 degrees. So alpha is going to be 180 minus 13.9 degrees. And so our angle is 166.1 degrees. So now this is our angle to the positive x-axis. For the magnitude, we are just taking the magnitude of the vectors a plus b, which will give us the square root of negative 350 squared plus the quantity 50 root 3 squared. Let's round this to the nearest tenth. And so the magnitude of these forces is about 360.6 newtons. And now on the last step of the problem, we'll make sure our force is in newtons because that is what we were given in the problem. So we found our angle and magnitude of the resultant force. Last problem, example 10, a 100-pound weight hangs from two wires as shown. Find the tensions, the forces in T1 and T2 in both wires and the magnitudes of the tensions. So when we say the tensions, because this T1 and T2 are capital, we really want these in vector form. We want those vectors and the magnitudes of the tensions. So let's do a little bit of sketching here. So if I have these two tensions, I'm now solving for two unknowns. They're pulling this weight up and over in this direction. And when I'm looking for the horizontal and vertical components of T1, I'm going to draw a right triangle like so. horizontal and vertical components of T2, triangle like so. Now, going back to geometry, if this angle's 50 degrees, and I'm assuming that this line is horizontal and this line is horizontal, if I have two horizontal lines, so two lines are parallel, then we have those opposite interior angles which are congruent. So this 50 degrees is the same as this 50 degrees. Likewise, this 32 degrees is the same as this 32 degrees. So just going back to basic geometry here. And this is a right triangle. And so using that, I can write equations for T1 and T2 with the horizontal and vertical components in mind. All right? So my first equation is going to be T1 is equal to, and this is going to be that vector. T1 is going to be equal to, well, in the x direction, I'm going to have the resultant force in the negative x direction, and that resultant force is the magnitude of T1 in the negative x direction times the cosine of 50 degrees. All right, and I'll write these using that I and j notation. It does not matter. So this is the horizontal component of T1, and then we are adding to that the vertical component of T1. Now we can see T1 is pointing upwards, so that's going to be the magnitude of T1 times the sine of 50 degrees. J, because that's the vertical component, I'm sorry. And now we're going to do the same thing with T2. So that vector, in this case, my x is going in the positive direction. So we have positive the magnitude of T2, which is the resultant force, times the cosine of 32 degrees in the x direction. And I can see that my y component is also positive, so plus the magnitude of T2 times the sine of 32 degrees. All right. Now, this is the most important part of setting up the problem. From now on, it's just going to be a lot of algebraic manipulation, but this is the most important part. We're just creating vectors for T1 and T2, just using that general formula to break these up into their horizontal and vertical components. So we're just using this and saying, okay, we don't know what T1 and T2 is yet, so I'll just call this the magnitude of T1 because the magnitude is the force. All right. So now let's see if we can simplify these any further. Now to solve this system of equations, we're going to only need to be left with two unknown variables. So we just want to be left with the magnitudes. So what is T1 and what is T2? Well, what do we know about a hanging weight? We know if a weight is hanging, then the force pulling up on this weight is equal to the force pulling down on this weight. That's the definition of any kind of still object. It means the force pulling up on it by whatever's holding it is equal to the force pulling down on it by gravity. All right? So now I'm looking at my j components. I'm saying, well, isn't the sum of these j components equal to 100 pounds if this weight is still? And so this is going to be my first equation. I'm saying that the j component, so absolute value, oh my goodness, magnitude of T1 times the sine of 50 degrees plus the magnitude of T2 times the sine of 32 degrees is equal to 100. Right, so this is just saying that this weight is neither rising nor falling. Now what about the horizontal components of this weight? Because I know that these two forces are pulling against this weight in opposite directions, horizontally, right? I also know that since this weight isn't swinging around back and forth, that means the horizontal components must be equal. And so my second equation will come from these horizontal components being equal to each other. So we have T1 times the cosine of 50 degrees is equal to the magnitude of T2 times the cosine of 32 degrees. Now you might be asking, where did this negative go? Well, I'm really just setting these equal to each other. Another way I could say it is that negative magnitude T1 cosine 50 degrees plus magnitude of T2 cosine 32 is equal to 0. This is just a different way to write that, so don't let dropping that negative confuse you. So now I've got two equations, I've got two unknowns, so now we're going through a basic solving a system of equations. And we can use different methods for solving a system of equations. I'll use the substitution method. I really don't want to try to eliminate any of these. And so let's just start with the second equation, and I'll isolate, I don't know, T2. All right, so manipulating this second equation, if I want to isolate T2, I should really say the magnitude of T2. I'll divide both sides by cosine of 32. So I can say that T2 is the same as the magnitude of T1 times the cosine of 50 degrees divided by the cosine of 32 degrees. All right, so now that we've solved the second equation for the magnitude of T2, let's then plug this into equation 1. And so we get the magnitude of T1 times the sine of 50 degrees plus, now instead of the magnitude of T2, I'll write this expression, magnitude of T1 cosine of 50 degrees over cosine of 32 degrees times the sine of 32 degrees is equal to 100. Now we've only got one unknown, so now let's solve this equation. And to solve this equation, I can factor T1 out of both sides. That magnitude of T1 times the quantity of sine of 50 degrees plus cosine of 50 degrees times the sine of 32 degrees over the cosine of 32 degrees. And yeah, you can just call this the tangent of 32 degrees at this point, is equal to 100. And now let's evaluate this in our calculator. Unfortunately, I do not have an emulator at home. When I plug this in my calculator, making sure I'm in degrees, I get the magnitude of T1 times 1.168 is equal to 100. Dividing both sides by 1.168, I get that the magnitude of T1 is equal to about 85.6, and our units are in pounds. Great, so that's T1. We can get T2 just by using any one of these equations. So to get T2, I'll use this over here and find that the magnitude of T2 is equal to 85.6 times the cosine of 50 degrees divided by the cosine of 32 degrees. All right, note, be very careful here. With your calculator, make sure you don't round intermediate steps. I'll write a note here for those of you who are looking at the notes. Don't round intermediate steps. So while it looks like I'm taking this and I'm rounding it to 85.6, I'm just going to use this initial value, this actual value in my calculator. And it's really something like 85.638. so on. So I'm just going to leave this up in my calculator, multiply it by the cosine of 50, and divide that by the cosine of 32. Because we want to be very careful that we don't have any kind of rounding errors, especially because WebSign's a little picky on that. And so I get that the magnitude of T2 is 64.9 pounds. All right, so let's see what the question wanted. Great, we found the magnitude of the tensions. So these are the magnitudes of the tensions. And how do we find the actual forces, that vector form of those forces? Well, we have it up here. That the vector form of T1 is equal to negative magnitude of T1, so 85.6, times the cosine of 50, I, plus 85.6 times the sine of 50 degrees J. Again, not rounding here, just looking for that 85.6 something in my calculator. So I'm taking that, multiplying it by cosine 50, and I get 55.047, and so the vector of T1 is going to be negative 55.0I, and then for my J component, it's going to be 85.6 times the sine of 50, which is going to be a positive 65.6 J. So this is my vector for tension 1. For tension 2, I have T2 cosine 32I plus T2 sine of 32J, and I'm going to do the same thing here. To find that vector of T2, I'm going to have, let's see, T2, the magnitude was 64.9, times the cosine of 32I plus 64.9 times the sine of 32 degrees in the J direction. Just a quick calculation here. All right, this gives us that that vector is 55.0 in the I direction. And 34.4 in the J direction. And you might have noticed something a little bit strange. So you might notice that these x components are exactly the same, but isn't that what we said? That these x components were going to be exactly the same so that this doesn't sway, and our y components are slightly different, and that's because we have different angles here. And this kind of comes into play more in the engineering field, but just something to note. It tells us that there is less tension on the wire with the smaller angle to the horizontal. So this comes to play in engineering, you know, when you have to decide which types of wires to use, you know, what tension rating you need. So you will use this if you're going into anything like that. All right, that is it for section 12.2. Thank you for watching, and make sure to do your homework.